understand why the text box is so hard to read. Sarah, I don't know if you can hear me at all. Mine says that it's live and streaming. Hi, Annie. Hopefully Sarah can see me. Still trying to fix that text box. I can't figure out how to make it like so you can read it real easy. Kaylee got her own page now, her own YouTube account. I'm proud of you. Okay. Going to try this. Hello. All right. Well, ask me questions. There are several of us now. See if I can fix it on this one too. I guess I just have to make the box bigger. Okay. Hi, Annie. For hydrogenation, would a benzene be turned into a cyclohexane? There is a way you can do hydrogenation with benzene rings, but we didn't cover it, and it's not with the reaction conditions that we've looked at specifically. So you can kind of ignore it for now. If you do the Googling for hydrogenation of benzene, you'll see that you can do it, but you have to use a lot of really high pressure. The first one that comes up is from a journal talking about hydrogenating benzene with nickel and palladium catalysts. I'm not really concerned that y'all know that, so you can just kind of ignore it. Essentially, what we've done, you won't be able to do hydrogenation with those reaction conditions on a benzene, just an alkene or an alkyne. Hope that makes sense. I have Sarah, Annie, Caitlin, and Hannah. Hi, Hannah. Do I need to check my email? It's usually a good thing because some people send me questions. It doesn't happen often, but sometimes. Oh, just Or am I online yet? Yes, yes I am. It seems like there might be a bigger delay than normal. I have no idea what factors contribute to that. It's very weird. Whoa, that is a... Hold on just a second. I'm trying to make sure you guys can see all the questions. The problem is it's a really long box. Okay, well, we'll just do it this way. Oh, and Charlene is here, and Kaylee is here. So, orthopara, keep getting confused on where to place my atoms. There's nothing I can really say for that that's going to like super clarify anything in a way that we haven't already talked about. You just need to know that if you have a benzene ring with something on it, and it doesn't matter what that something is, we can just call it X. So if you have something attached at the first position coming off, you would call that the ortho position. If you have something coming off at the second carbon away, that's the meta position, and then the para position is the one on top. So, I mean, you basically just have to memorize what those terms mean. There's not really another way to do it. I told you guys the way that I tend to remember it is to think of Willy Wonka's Oompa Loompas, because OMP, that's like the only way I could remember those, the order for those. So OMP going around the ring, and it doesn't matter which way you go around because there's 2 ortho positions, 2 meta positions, and 1 para position. So hopefully that makes sense. If you have something, if you're doing a reaction and what you have on there is an ortho-para director, then that means you're going to get a mixture of products. Some will be in the ortho position and some will be in the para position. If you have something that's a meta director, it only goes on the meta position. And we talked about the reasons for that in class with the resonance structures that we covered for the intermediate on that. For an acetal, would we show the hemiacetal part? So Annie, if you're doing the mechanism for an acetal, you'll show the hemiacetal formation in between, but we're not going to have, if you're just filling in a problem, you know, you're going to make the assumption that it'll go all the way to the acetal position. Okay. Can I go over the Huckel rule question? Go over a Huckel rule question. Okay. Let me pull this up. Do it this way. You know what? I'm just going to make it up there. I'll move me down here. I don't like it when you guys can't see me when I'm talking to you. It feels weird. My goodness, is there a reason that is so big? Can I change this? Oh, I can. Ah, look at that! Internet works again. Oh, good. Okay. So hopefully you guys can see and read. I was looking at it and it didn't look like you'd be able to like read the chat log if you were watching this after the fact. Okay, so a Huckel rule question. So let me bring up my paint. So you're basically just looking at how many electrons are going to be contributing for resonance in something that meets the criteria for resonance. So you have to, or for aromaticity. So you basically need to think about kind of a checklist of things for, is it aromatic? Okay. And so the first thing that would be useful is to look at whether or not it is cyclic. If it's not cyclic, then it can't be aromatic. That's kind of the basic bottom of the line definition, okay? Must be cyclic. The next thing is, does it have conjugated electrons in pi bonds or lone pair? You could have some that don't have lone pair. We're not going to get into anything like that. I'm not going through it. I don't even do that in the regular organic class. So after you have that criteria, so is it cyclic? Yes. Does it have a conjugated electrons in either pi bonds or lone pair electrons? Yes. Then you need to apply the Huckel's rule. And so if you remember, Huckel's rule basically tells us whether or not there's a correct number of electrons in the ring that will contribute to it being aromatic. Huckel was the name of a scientist who came up with this many years ago. He kind of did some experiments and found out that, so for, he would do this one. Let me draw you guys a picture to try and give you a little more context. There we go. I'm having like computer problems today. I'm sorry. Okay. So what he would do would look at something like this molecule here. Okay. Now, if you consider the first two of those kind of criteria, is it cyclic? Yes. Does it have conjugated electrons in pi bonds or in lone pair electrons? Yes, in this case, all pi bonds. But he would notice that they would undergo reactions similar to alkenes. So, you know, like with alkenes, we learned how to do all those electrophilic addition reactions, right? Like the hydrohalogenation reaction, things like that. Benzene doesn't do those chemistry. It doesn't do that type of chemistry, but the molecule that I have on the screen right now does. And so that's where Huckel's rule came into play, because you could definitely have conjugated electrons, you know, in resonance circling around that ring, but that doesn't necessarily mean that it's going to be acting like an aromatic molecule does, meaning having all that extra stability we think of with aromatic systems, okay? So, let me pull back my text box here. So if you try to fill in Huckel's rule for the molecule above, you would basically have 4n plus 2 equals question mark. And the question mark is the number of electrons that you have in that conjugated system. So in this case, it would be 8 electrons, okay? If you take 8 minus 2, that's 6, so 4n equals 6. And that would mean n would be equal to 6 over 4, which is what? 3 halves, so 1.5. If it's not a whole number, a whole integer, then it doesn't fulfill Huckel's rule, okay? So if you compare that with like benzene, or anything else essentially that's going to have 6 electrons, so let's do an example here with nitrogens in the ring, okay? There's still lone pair electrons on this nitrogen, but those don't really matter because, excuse me, I have 2, 4, 6 electrons there in the ring. 6 electrons in a ring cycling around will fulfill Huckel's rule the same way benzene does. Okay, where 4n plus 2 equals 6, and then n equals 1. So I hope that kind of makes sense. The movement of the pi bonds is just standard resonance, like what we did early in the beginning of the semester. Here I'll give you 2 examples. So these electrons could come in here. Well, if that happens, the nitrogen there on the top is going to have too many bonds, so these electrons will move over, and these electrons will move over. And so they'll just keep cycling around. Alternatively, can you guys... Okay, you can see that. Hold on. So alternatively, you could also go the opposite way. And both of those are perfectly acceptable, and it doesn't really matter. So as long as you're kind of able to move those electrons around, you should be good. Another example, you can talk to your mom. It's okay, Annie, she'll be all right. So let's look at an example here with, let's see, let's do one with 2 nitrogens in it. Double bond there, double bond there. Poor mom. Okay. So that's actually a structure called imidazole. It is the core of the structure for the amino acid histidine, actually, so you guys will be learning that next semester. And so what I'm going to point out here is that here's another system that has 2, 4, 6 electrons, okay? And so if you're wanting to show the resonance with that, with the lone pair, you can do it the same way. It doesn't matter if you start going from the left or to the right. It's kind of the same kind of deal. And you just kind of go around the circle. So if you do that, let me draw my product. So now I'll have a bond here. What did I just do? What have I done? There's something that looks wrong about this. Hannah, yeah, so that's typical. If you don't show them that way, it would be kind of weird. I mean, I guess technically you don't have to, but pretty much everybody would. I don't know what I did wrong here. Now I'm embarrassed. I don't like it when I mess things up for you guys. Oh, I know what I did. I just didn't put the formal charge on it. Let me fix that. Okay. So now it's a positive charge, then the electrons go up here and make a negative on the carbon, like that. Okay. I fixed it. Okay. So these are the 2 resonance structures that you would expect to see for imidazole. Okay. So I hope that kind of gives you a little bit more for examples on how to do aromatic, like determining if something's aromatic or not. Let me know if that answered your question. I feel like I've been talking about aromatic stuff now for like 85 minutes, so. I'm looking to see. Are the lone pair electrons inside when the nitrogen is attached to a hydrogen? Okay, so the answer for that is if it makes it fit Huckel's rule, then yes. If not, then no. So remember that, you know, you basically want to always make something aromatic if it can be. I said that in class a few times. If something can be made aromatic, it will be. So if you need those electrons to make it aromatic, they'll be in the ring. And if they don't need to be used to make it aromatic, then they won't be. Which I know probably sounds like a really weird answer, but it's what the experimental evidence has shown us. There was an example of an acylation reaction, and it didn't use a benzene ring on one of the practice tests. An acylation reaction that didn't use a benzene ring. I don't know what you're talking about because that's the only one that we've learned in class. We haven't done any acylation reactions without a benzene ring, so as far as I'm concerned, just do ones with benzene rings. Okay. Yes, Kaylee, that will be good in the hood. Now, I'll just add on to that, Sarah. So you said an acylation reaction that didn't use a benzene ring. So an example, let me make sure I have the screen up right. Okay. So something I could do is something like this. Where you're essentially starting off with the acid chloride, and then, right, you would need to add the benzene rather than taking the benzene and adding the acid chloride to that. Yeah. But that's the only thing I can think of like that. And then you would need to add in your catalyst, AlCl3, the aluminum trichloride. I don't have any of the old exams sitting in front of me. And then, is 2-hydroxypentanoic acid chloride something we've learned how to draw? Well, we've learned how to draw it, but we haven't really learned how to name it. I pointed out various functional groups, right? So we learned what an acid chloride is, but I didn't really cover, unless I'm mistaken, I don't think we covered how to name them. Not in our class, I did it in the regular organic. So if I have pentanoic acid, it would just have the OH at the end. Pentanoic acid chloride would be kind of a common name. It would actually be 2-hydroxypentanoyl chloride. That's how most people would pronounce or name it. And it would look like that. But I mean, context clues, I would guess you could answer that, but that wouldn't be a question I would ask you guys because we haven't covered it explicitly. Oh, I know what happened. I did the thing where I made it big again. It's really weird. The program I use, if you don't change the, or if you change the size of the screens you're using, it changes it on the feed. It's kind of annoying. I was hoping they'd fix that in the update. They did not. Two hydroxybutanoic acid. No, Caitlin, because it had the Cl at the end, not no H. Careful when you look at it. Is para-hydroxyethylbenzene, the same as 4-ethylphenol. Yeah. So here. Come on, there you go. Okay. So if I have, let's just compare these. So para-hydroxyethylbenzene, meaning I've got things in the para positions, an ethyl group and a hydroxyl group. The next one is phenol, which I know starts off looking like that. So that's 1, 2, 3, 4 ethyl phenol. So yeah, it's the same thing. Oh, David's here. Hi, David. An acetal mechanism? I can. That'll take a minute, so pull on your bootstraps. And then let me think that's big enough. I think I'm going to make a new. Give me just a second. I know you can't see me. If the screen just went black, don't worry. Just hang in there, kids. I'll be there in just a second. Okay. So hopefully you can still hear me and still see me. I just wanted to give us a bigger platform to write on. So I'm still hearing everything. I can click back to the other ones, but I wanted to have a bigger canvas to kind of do this because it's such a big mechanism. Okay, so if we want to do an acetal, we need to start off with either an aldehyde or a ketone, right? And an alcohol and a little bit of acid catalyst. So those are the components that you need to do an acetal reaction. I'll just go ahead and type those in here. So you need, I mean, you can almost think of these as like baking a cake. Like, what do you need? You need 2 eggs and some flour, right? So for an acetal, you need a carbonyl in the way of an aldehyde or ketone. You need an alcohol, and you need some acid catalyst, which I'll just put down as H+, because hopefully you've kind of gotten to the point where you're realizing that sometimes the actual acid you use isn't nearly as important as the fact that you're just adding a little bit, you know, a couple drops of acid to catalyze a reaction. So let's do, and I'll try and color code it. Okay, so let's say I have, hold on. Okay, so if I have some sort of, whoops, come on, there we go. Let's see, some sort of, yeah, I'll just do it that way. So this would be cyclopentanone, okay? So this would be the ketone in our acetal reaction. And we need to add in some sort of alcohol, and it's almost Christmas, so I'm going to go with red and green, because you can be festive when you do organic chemistry, if you didn't know. And then my acid catalyst. And I'm just going to click back on my screen real quick to make sure you guys can see that. Okay, looks all right. Okay, so the first thing that happens is you're going to protonate the ketone or aldehyde, whichever one's there, using the H+. So, whoop, There we go. Now this is one of the ones where it would behoove you to draw it with reversible arrows because it's technically reversible. Okay, and if you remember, that's why I said your body has that alpha and beta form of glucose, because that's a hemiacetal and it can flip back and forth that way. Okay, so put our charge on the oxygen and we're good to go with the next step. So remember that a pi bond is going to be the easier of the bonds to break. And what's going to happen is a lone pair of electrons on the alcohol will attack that partially positive carbon. Remember that that one has a partial positive charge because it's a polar bond attached to an oxygen, right? That's going to push those electrons up onto the oxygen as a lone pair. Okay. And that's going to give us our product for that, which is going to need to be deprotonated. Now, you have base laying around, right? If you have H+, you have to have the B- that corresponds with that. It could be the conjugate base of whatever acid you used. We have alcohol in the system, we'll have water in the system. So any of those will make just whatever base you want to deprotonate. Oh goodness, I need to like run around there. Okay, so I'm going to deprotonate the alcohol. And with that, the product that's formed, let me make that a little lower. The product that is formed is the hemiacetal. And if you called this a hemiketal, you would not be incorrect either, because we started off with a ketone. So if you remember, we talked about how that was one of the possibilities that you could refer to this as either an acetal or a ketal if it specifically came from a ketone. Okay, so then the next step, also reversible, is to protonate the alcohol again. Or rather, for the first time, but we're protonating that oxygen again. Okay. And I'm just going to put that as OH2 for brevity's sake. But now with that, you have a good leaving group, right? Water's a good leaving group. And what that means is that you can have a second molecule of alcohol come in and attack that carbon with the partial positive on it. That carbon still has a partial positive on it. It's probably even more so now because it has two oxygens connected to it instead of just one, right? So that'll kick off. I'm running out of room. I'm sorry, guys. Okay, and then the last step then would just be for base to deprotonate that again. And once again, I'm sorry that this is kind of so everywhere. Whoop, there we go. I'll deprotonate that. Put the electrons on the oxygen. And then I get my product. I'm going to use shorthand here. ME means methyl. That's a common abbreviation that you can use. It's not one that I often use, but okay. So now this is where I click back to make sure everything was on the screen. Yes, it is. And now I check the text box. Oh, yeah. Cyclohexanone. You're right, Hannah. Sorry. So hopefully that... Wow, that looks ultra festive. That's pretty festive chemistry, right? Hopefully that makes sense. Sarah, can I get some confirmation on what I just did? Or anyone for that matter? Okay, good. Thank you. I'm like, hello? Wait, who's Cupcake Queen? Is that Charlene? Charlene, are you Cupcake Queen? Is that who you said? Yeah, well, Kaylee, that's just an issue. I can circle the hemiacetal. Hannah, can you? Huh? I'll give you guys a second to look for it. And then I'll circle it. But yeah, Kaylee, a lot of this is just, you know, doing it enough times over and over so that you're comfortable enough with it that it kind of comes as second nature to you. If the hemiacetal is given as the product, we just stop there. Well, we have to go all the way to the acetal. Yeah, so if I give you a problem, you know, you can make the assumption that we're going to go all the way to the acetal. There have been some examples when I've done them on exams where I have asked, you know, just to show the mechanism to get to the hemiacetal part or whatever, just because it was shorter. So here we go. So there's our hemiketal or hemiacetal. I keep circling it because it's kind of fun doing this on my screen. So that's the hemi, and then this is the full acetal. You can pick these out because they're all going to have something in common. You're going to have a carbon bound to 2 oxygens. Okay. One of those, if it has an R group and the other one has a hydrogen, you're going to be looking at the hemiacetal. And if it has 2 R groups, then you're looking at the acetal. Okay. So that's kind of just knowing what to look for on that example. Anyways, like draw an actual B- on the paper. Can I just add B- to cause the water to leave? Or do you have to draw arrows from the CH3OH? Sorry, hold on, Caitlin. I'm trying to interpret your question. The base is not causing water to leave. So notice that is very specifically the alcohol, because you need to form the bond there with the alcohol. So you actually need to show the alcohol forming the bond. Any of the deprotonation steps, you can feel free to use either a B- or you can use the CH3OH as your base if you want. But when you're talking about this arrow specifically that I'm kind of highlighting there, you have to show that the same as this one here. Okay, because it's not a base attacking it, it's an alcohol attacking it. Okay, more questions. Go back to my... Yeah. Here, I'll give you guys another one, and then I'm going to run and grab something to drink because my voice is kind of like in desperate need of water. Okay, so we did a few different reactions, right? With ketones and aldehydes. So I'm going to give us, oh, come on. that one. IUPAC name, methanal. Common name, formaldehyde. So I want you to do a reaction where you add ammonia. I want you to do a reaction where you add phenol. So work on those, and I will be right back. Sorry guys, I just sat back down. Cute try, Hannah. All I want for Christmas is my organic answers. My organic answers. You guys are funny. Look, I have a festive cup. Look at that. Ah, where's the... Isn't it cute? We never get any snow here like this, but that's okay. I can live vicariously through my dishes. It's probably better than me singing the nucleophile ataxia electrophile song, which is literally just the same lyrics over and over again. But you know what? One of my research students who didn't have me for organic, but she came up to me I think the second month of this semester, and she was like, is it the nucleophile ataxia electrophile or the other way around? I was like, you haven't heard the song, have you? What do y'all think? Man, there's like so much glare on my glasses. If I sit down like that. I get a little slap happy at night. You are not doomed. You guys are being babies. You can do this. This whole semester, it's, I don't know what I'm doing. And then you guys keep rocking all the exams. No pity for you. You do got this, Caitlin. You got this. All of you. All right, let's go. Let's do those problems. Let me grab the big screen again. So for the record, and I don't know if you're aware of this or not, but when I have the screen set like this, I basically can't see or do anything with the chat box right now. I can't see it, so if you guys have questions, you'll just have to give me a second for the delayed response. Okay, so let's do the top one. If you looked at this top problem and thought, what type of reaction is that? And you thought, imine, then you're correct. And on the bottom one, if you were like, acetal, then you were correct. Okay? So, the same way that an acetal is an aldehyde plus an alcohol and some acid, an imine is an aldehyde or ketone, an amine, and some acid, okay? So imines are pretty simple. The mechanism takes a long time because it's just a lot of protonations and deprotonations, but essentially you're having to replace that nitrogen with that oxygen and you get water out on the other side, right? So all I'm going to do is replace that with nitrogen. Because it has hydrogens on it, that's what's still going to be on the nitrogen. That's the product, okay? I'm going to fix my arrow there to make it reversible, and then you get water as your byproduct, okay? Now we did that mechanism. I don't think we need to do it again. You can look it up if you want, if you were missing class that day. It takes a while, and I don't have that much time left with you guys, but you know, just realize that it's a bunch of protonations, then deprotonate. Protonate, then deprotonate, protonate, then deprotonate. It's pretty much the majority of it, with an exception of when the nitrogen attacks and when the water leaves. So just kind of keep that in mind. Now, the other one is instead of, let me grab a different color. So instead of having a nitrogen attack, what we're going to have is here where that carbon is, we're going to stick that oxygen on there, okay? So that's another way to look at this. Now, it's going to be kind of different looking at it that way than when you do the mechanism, probably. But remember, an acetal is a carbon bound to 2 oxygens, and those oxygens were alcohols. So you're just going to put on whatever was attached to that alcohol, and there you go. We could draw that all kinds of ways, but I'll just leave it like that. You also get water as a byproduct here. So if you looked at this and got this right, congratulations. Yeah, and so if we had anything else, let's do a different example for that. So, actually, I'll just delete that whole thing. So let's say I'm doing formaldehyde again, okay, and this time the amine that I want to use is, let's do something bigger than what we've been doing. That just does not look good. Let me try that again. Okay. So as long as you have 2 hydrogens to come off, right? So remember that on this side over here you get water. Well, what is the water coming from, right? The H2O is the oxygen and then the 2 hydrogens there essentially. Right? We use H plus as a catalyst here to make the reaction go, but in actuality, it's really just OH2 or H2O, you know, coming off. So remember that, and that's where the nitrogen gets stuck, right? So then I end up with an H, a C, an H, and now instead of a double bond to the oxygen, I have a double bond to the nitrogen. The 2 hydrogens came off. And now I'm left with this. You can draw a lone pair on there if you like them. I know some of you guys like to show your lone pair, and that's fine. But that's what you would get. And that R group can be anything. If you get into reactions that I don't cover with you guys, there's something called an enamine, which is closer to an enol. And that can happen if you have something that has a nitrogen on it that has less than one, or I'm sorry, more than one R group on it. but that's not something we've covered, so I'm deleting it. But if you're seeing something like that online, it's probably an enamine. You do not have to show the water as a product in the answer. I'm just putting it on there just to remind you guys that it does come off that way. David's been quiet tonight. David, are you still there? And Caitlin, I've probably mentioned it before, but as a general rule, and for all you guys to remember this, generally speaking, most organic chemists for their products only put the organic molecules that you get as products. So in some cases that can be multiple products, like if you do an aromatic substitution and you get orthopara products. So, right, you would show both of those, but you don't have to show, you know, getting the catalyst back at the end and any of the HCl, that kind of thing. Hannah had a light bulb moment. I can draw that. So let's see. Here's Hannah. Oh, maybe I can't draw that. I'm not good at drawing. Here's Hannah. And she's got long brown hair. She's adorable. And she had a light bulb. That's supposed to look like a light bulb. It may or may not. I'm not good at drawing on these screens. I'm using my fingers, so that's probably why. At least that's what I'll do on. David, I read that in your voice and it made it even more funny. Now, Caitlin, one thing that I'll point out also, if you put them on there, I never count off. So if you like having them there, you know, you can always show them there. I'm fine with that, but you don't have to. I know some organic professors do require it, but since it's not really convention in organic chemistry literature to do it that way, I try not to do it in class, but yeah, no, it's up to you. Let me double check my email real quick, make sure nobody's trying to get in touch and ask questions. Is Wee with us tonight? Oh, Casey's here. Hi, Casey. Yeah, for all of the electrophilic aromatic substitution reactions, you will want to show the mechanism, including the formation of the electrophile. So for the nitration reaction, you know, that involves the nitric acid, and the sulfuric acid, and that's just part of the mechanism. So you'll want to go ahead and keep that in there. The same with the Friedel-Crafts reactions where you're using the Lewis acids. Wow, that was a bad arrow. There we go. Whoop. Now something you can do if you want to kind of shorthand it is just write that as water. Like that, to form the nitronium ion. I'm writing love notes to chemistry now while you guys don't answer or don't ask me any questions. And I cherish and appreciate you, Caitlin. I love you guys. You're fun. Well, it's 8 o'clock. I guess I'll go ahead and let you guys go. I will be on campus tomorrow if you need me. I have class from 10 until 11ish, and then I have a break for an hour. I was going to try and eat in my office though, and then I have APSU 1000. Pray for me. I have my last APSU 1000 class tomorrow, right before your class, but I'm hoping, since it's their last class, I'm hoping to get done either early or leave them with the mentor, the student mentor, peer mentor in there. So hopefully I'll be in my office about a half hour before your class starts. So hit me up if you need me. And I'll be up for the next few hours. If you guys need help, you can email me, okay? Good night, Brief Organic Chemistry.